In this video of information theory and coding, today we will learn about convolution codes. Brief introduction of convolution codes. Now in convolution codes, the block of n code bits generated by the encoder in a particular time slot depends not only on the block of k message bits within that time instant but also on the preceding m-1 blocks of message bits. Here, the input bits are stored in fixed length shift registers, and the shift registers, as you know, are made up of flip-flops and shifts the bits one register to another at every time slot. Now, coding depends on current bit and the previous bits. These are combined together and encoding is done. Convolution encoder is a finite state machine, that is FSM, processing information bits in a serial manner. Convolutional encoding of data is accomplished using a shift register and associated combinational logic that performs modulo 2 addition. Let us consider this example of convolutional encoder. Here, current bit is M and we have previous bits M1 and M2. For each time slot, input bit is given to M. The shift register shifts contents of M to M1 and contents of M1 to M2. Here we have two outputs V1 and V2. From the first modulo 2 adder, we get V1 is equal to M modulo 2 addition with M1 modulo 2 addition with M2. And from the second modulo 2 adder, we get V2 is equal to M modulo 2 addition with M2. The output switch first samples V1 and then V2. Hence the output bit stream for successive input bits will be X is equal to V1 V2, V1 V2, V1 V2 and so on. Here it may be noted that for every input message bit, two encoded output bits V1 and V2 are transmitted. Let us learn some of the important terms related to convolutional codes. First one is code rate, denoted by R. Now the small r is equal to small k divided by small n. What is this k? K is the number of message bits and n is the number of encoded bits per message bits. In our previous example of convolutional encoder, at every time slot we had one message input bit entered into the encoder. So we have k is equal to 1, it was processed and we were getting two outputs V1 and V2. So we have n is equal to 2. So the code rate is equal to 1 divided by 2. Second term is the constraint length denoted by capital K. It is defined as the number of shifts over which a single message bit can influence the encoder output. Now in our previous example, observe that whenever a particular message bit enters a shift register, it remains in the shift register for 3 shifts. That is, first shift will be message bit is entered in position M. Second shift, message bit is shifted in position M1. Third shift, message bit is shifted in position M2. And at the fourth shift, the message bit is discarded or simply lost. We know that V1 and V2 are combinations of M, M1 and M2. Since a single message bit remains in M during first shift, in M1 during second shift and in M2 during third shift, it influences output V1 and V2 for 3 successive shifts. So we have k is equal to 3 bits. This is because in this encoder, a single message bit influences encoder output for 3 successive shifts. The third term is code dimension. That is the dimension of the code given by n, k. We know that n is the number of encoded bits per message bits and k represents the number of message bits taken at a time by the encoder. Now in our example of convolutional encoder, we had number of input bit per time slot, that is k was equal to 1, and the number of output bits was n is equal to 2. So the dimension of the convolutional encoder is 2, 1. In our next video, we will see how to draw code tree for the convolutional codes. Thank you.